Okay, so let us do a very quick recap of last lecture. Essentially the previous lecture was the Viterbi algorithm. Okay, which is soft ML decoding, or let me just say ML decoding, even for the hard version something works. Of convolutional codes. Okay. So in fact anything that you can represent on a trellis with putting weights on the branches, and then you want to find the path with minimum branch weights, okay, with some of minimum path weights, you can use the Viterbi algorithm. So for instance in the equalization problem for ISI channels and digital communication, people use Viterbi algorithm. Okay, so that also you have a trellis, natural trellis representation on which you can do, you have to find the minimum weight path. Okay, so and even if you are going from, let us say, Delhi to Chennai on the road, there are multiple cities that you can go through in the middle. You want to find the minimum distance path from Delhi to Chennai. I am sorry, traveling salesman. Oh, traveling salesman is more complicated. Let us not go there. Okay, it's much more complicated. There's no efficient algorithm for that, but this is just point to point. Yeah, point to point, 1 point to 1 point. So those things you can do using a Viterbi like algorithm, which is also other algorithms for it, but this is, so the reason I am saying this is, all this is, it's just one instance of a very popular algorithm from other area, okay, some other areas. So it's beneficial to learn other areas, is all that I am saying. Okay, so you learn some other area, some other type of algorithm, you might be able to use it for decoding, who knows. Okay, so we have to talk a little bit about performance. Okay, and we will use the union bound kind of argument. If you remember, for the ML decoding, soft ML decoding for linear block codes, which is what Viterbi algorithm is doing, right? Convolutional code is after all a linear block code, okay, when you implement it with finite length, and when you do ML decoding, the behavior can be nicely captured using the union bound estimate, okay, which is one way of doing it, and the union bound estimate will have this form, okay, assuming I can write it correctly. Union bound estimate, okay, you remember what form it has. There will be two terms, right? There will be first an A and then a Q, what, remember something here? Yeah, so d min will enter the picture, right? So minimum distance will enter the picture. So basically this will be this Q will basically be the pairwise error probability, right? What, so this will be kind of distance between shortest distance between two code words, right? So let me write that down here. What comes here is something that depends on the shortest distance between, shortest Euclidean distance, right? Remember, we were visualizing that each code word or symbol vector is some point in a large n dimensional space, and if you want to find a pairwise error probability, what is the if given that something was transmitted, how will you mistake it for some other specific vector? Then all you have to do is only a one dimensional Gaussian detection, right? So you look at the distance between these two, and Q of that distance by 2 will give you the probability. Okay, so what enters here is shortest Euclidean distance between any two symbol vectors, right? Okay, so that is what will enter the Q. What will be A? Okay, that is where the union bound comes in. So here they will have the number of closest neighbors. Okay, so if you have to do a union bound estimate for the Viterbi algorithm, you have to first find the closest code word or the distance between two closest code words in a convolutional code. Okay, that is something you have to find, and then you also have to find how many such code words are there. Okay, so if you have, let us say, the all 0 code word. All 0 code word is a good place to start. Okay, you have the all 0 code word, and then what are the code words of least weight, and how many of them are there, and what are they? Okay, what is the weight exactly? So that's all you need to find. Once you find that, then you can figure out the union bound estimate, which gives you a good handle on the soft ML decoding. Okay, so it's pretty good. So indirectly, what we are doing in this analysis is also trying to solve a design problem. If you can do this very nicely, then what should you be able to do? You should be able to come up with a convolutional encoder which will give you the best possible union bound estimate. Okay, how will you get the best possible union bound estimate? You have to maximize the distance between the two shortest vectors, and then what else should try to do? You should try and minimize the number of closest neighbors. So we will see that this number of closest neighbors is not very easy to minimize in a convolutional code. Okay, so that will be very large. Okay, and that we will have to, well, reasonably large, at least it will grow, and but the Euclidean distance you can try and maximize. Okay, and in fact there are no nice closed form methods available for this. Okay, so you have to do a brute force search. So it's pretty much done using, come up with one encoder after another. Okay, given a certain memory, you can exhaust all possible convolutional encoders, right? How will you exhaust all possible convolutional encoders? Just a question of all possible connections. Okay, so you exhaust all possibilities and find this distance for each of them. There is an algorithm for doing that, and then find that encoder which gives you the maximum distance for a particular memory. Okay, so you can do all of that. Okay, so this finding the performance or the union bound estimate also gives you a handle on designing good convolutional encoders. Okay, so that is something that goes along with it, but let us see how to figure out the shortest Euclidean distance. Okay, so I am going to do it very roughly in an intuitive way based on the trellis. Okay, there are rigorous guarantees for why this will work, and sometimes it can go wrong also, but roughly it will work in most cases. Okay, so let's see how that works. Okay, so what you have to do is to find minimum distance. Okay, so we have been assuming so far a feed forward shift register, right? There is no feedback link, and that is quite important. Later on we will change this and see what happens to some of the assumptions that we are making. Okay, so we are looking at a feed forward shift register. So if you look at the encoder, there is an input stream, there are a bunch of T flip flops. Okay, mu of them, and then what do? You have a bunch of outputs. Okay, and you have connections, right? And there are connections. Okay, this is how it looks. There is no feedback in this shift register. Okay, so you must have come across feedback shift registers also. It's possible to do a feedback, right? So you take some part of it and do it back. Okay, that also is possible, but we will look at feed forward shift registers for now, just to keep it simple. Okay, so in feed forward shift registers, trellises are very easy to come up with, right? Given a particular trellis, the next state is obvious, right? So you have to just shift and put in the zeros or the ones in the beginning. There is no problem. If you have feedback, then you have to worry about how that feedback is going to affect your next state. It is a bit more complicated. Okay, so let us first look at feed forward shift registers. So if you look at a trellis, you are going to start at the all 0 state, and it goes on and ends at the all 0 state. So the all 0 code word in a feed forward shift register will simply be a, well, in fact in anything I think all 0 is okay. All 0 will simply correspond to the top line. Is it okay? So in the trellis, the all 0 code word will show up on the top. Okay, and that will be a valid branch on any trellis. Okay, that will be something. So to find the closest code word to the all 0 code word, we will first deviate from a particular state. Okay, so let us start at the very beginning. I deviate, okay, and then all my inputs will be 0. Okay, so I have my first input as 1, okay, and it has some output corresponding to it, and then all my other inputs will be 0, which means what? Okay, I am trying to get back to the all 0 state, but in a feed forward thing, how many zeros will I need to get back to the all 0 state? I have already put in a 1, and then I will need mu of them, right? I have to put in mu zeros to flush out this one that got into the state. Okay, only then I will come back to the all 0 state, but it is all zeros. Okay. So, after mu 0 inputs, eventually I will come back to the all 0 state. Okay. So, here there are mu 0 inputs. Okay. All right. So, in most convolutional feed forward shift registers, I am not sure if it is true for all, this will be the minimum weight code word. Okay. The code word that you get on this path. Okay. So, you deviate from the all 0 path and then come back to the all 0 path by putting in zeros after that, you will get the minimum weight thing. Okay. So, I do not know if it is possible to come up with a diabolical encoder where you have to give in more than one input to get a minimum weight encoder. Maybe it is possible. I think this world is a little bit complicated, but if you design it decently, then this will be true. Okay. All right. At least one thing you can be sure of is this will give you a very low weight code word, right. If you just deviate once and then come back, after this you are all zeros. Okay. Output is all zeros. The output here might be something slightly non-zero. Okay. So, there will be some non-zeros here, zeros here, roughly half of them will be 1, half of them will be 0. Okay. So, clearly the weight here is going to be of the order of mu. Okay. And then even if you give as many inputs as you want, right. So, it will give you a low weight code word. Okay. And in many cases this will be the minimum weight code word also. We will simply take this as the minimum weight code word. Okay. So, in an exam question, if I ask you find the minimum distance, this is what you have to do. Okay. In a feed forward case, nothing else. Okay. Just go out and then come back to the all 0 state, figure out what weight you got, that will be your minimum weight code word. Okay. Is that clear? Okay. So, this path corresponds to the a low weight code word. We will take it as a minimum weight code word in this course at least. Okay. It is a good approximation anyway. Okay. So, it will be going to be a very low weight code word. Okay. Now, this fixes what goes inside the queue. Okay. What about the factor A? How many such things can you have? K, right, of the order of k, because I can do this deviation at any point, okay, and I can come back in mu states. So, my number of such low weight code words is going to be of the order of k at least. Okay, maybe k minus mu or something. I mean, if you want to be very careful, maybe k minus 1 or something like that. Okay. So, of the order of k it is going to be. Okay. So, this is a low weight code word. There are roughly k of them, maybe k minus 1 if you want to be exact, this variety. Okay. So, that is fairly large, I mean k is fairly large. If you go to 1000, there are 1000 such neighbors around all 0, okay, all looking to get your decision, right. I mean, they introduce errors, they are trying to pull the soft decoder towards the wrong decision. Okay. So, all these guys are bad for you, and there are so many of them, 1000. As you keep increasing k, it only grows. Okay. It does not become a constant or anything, and that is fairly bad. Okay. You can come up with other block codes for which this number is smaller than k, much smaller than k, you can do that. Okay. So, in your union bound estimate, what is outside the queue is pretty much out of your control in a convolutional code, at least with feed forward shift register, even otherwise you will see it is out of your control. Okay. What is inside you can control, okay, and that is the weight itself. Okay. So, what people do is they fix a memory and try all possible connections to figure out the best weight that you can get. Okay. And these things are available in tables. Okay. So, you will go look up either in Google or look up any book like Lynn and Costello's book, you will have a list of best convolutional codes for a particular rate for particular memory. Okay. So, that is what you have to pick, do not pick any other convolutional code. If you want a rate half code with memory 6, you go to that list, pick the best possible code which gives you a good minimum distance and use it. Okay. Or you can go to one of the standards and pick the codes that the standards is using. I am sure they would have done their homework well and they would know that what code will work. Okay. So, you go pick that and then you cannot go wrong. Okay. So, that is the crux of analyzing convolutional codes ML behavior and designing convolutional codes also. Okay. There is no rich theory behind the design of convolutional codes, simply do simulations and pick the best. Okay. If there is more than one possibility with the same code, then you have to do some exhaustive simulations, maybe there are some additional code words which give you some advantage, etc., etc. So all those second order effects can come in also, but usually this design is done based on the minimum distance. Okay. So that is where we will stop also, because this is kind of an old area and it is very well established. You pick up a book, you can read it very nicely, it is very simple and nice. So I do not want to go into great details over design of convolutional codes and all that. Okay, in fact I do not even know it is more information than this. There are some more things I know, but not too much, not too illuminating. Okay, so we will stop here as far as design of convolutional codes is concerned. Okay, so what we are going to do now is slowly move in a direction towards turbo codes. Okay, so what is it about convolutional codes that make it attractive for them to be part of turbo codes, which are there in every standard. Okay, so that is the kind of direction in which we are going to move, and for that we need to look at feedback shift registers also. Okay, so it turns out the using feed forward shift registers alone is not good enough when you want to try and reduce the number of low weight code words. Okay, so the low weight code word weight itself, okay, we have optimized to the best extent possible, but now if you want to do some design where maybe you decrease the number of low weight code words, it turns out you have to use feedback and you have to use some more other things. Okay, so not just one convolutional code, you have to use two convolutional codes and do some fancy tricks between them to get your number of code words down. Okay, so that plays a key role in the design of turbo codes. Okay, so we are going to move in that direction. So for that we have to look at what happens when you have feedback shift registers and not just feed forward shift registers. Okay, so that is the kind of that is the direction that we are going to take. Okay, so we will stop with decoding and performance at this point. Is that okay? So I am going to talk about that, and then we will go on and see what other ingredients are needed for turbo codes. Many more ingredients are needed, but we will start with this first ingredient, which is what role does feedback play and how is it going to change. Okay, okay. So we are going to go towards what are called as recursive convolutional encoders. So far we have been using feed forward. It's all actually feed forward is not a very common term. Non-recursive is the common term. Okay, so people usually say non-recursive, but we will now look at recursive convolutional encoders, and these play a very important role in the design of turbo codes. But before that, they also play an important role in one minor drawback of feed forward convolutional encoders. Okay, so here's the example that we have been looking at. The generator matrix has this form, right, 1 plus d squared 1 plus d plus d squared. Okay, this is the example that we have been looking at all along. So the one drawback here is it is not systematic. Okay, maybe it is not a big problem for you, but maybe it is something that you do not desire. Okay, so why is it not a big problem not being systematic? Yeah, can always get, but actually in the Viterbi decoder the message bit will anyway come. Okay, so you do not need to really make it systematic, right. Remember, it's just you are finding the path explicitly. The path has both the input and the output, so you do not have to really find the code word and invert from the Viterbi decoder. Okay, so it anyway gives you the bits. Okay, but anyway, so that is one point to address. Maybe you want to have systematic for other reasons. Okay, the other reasons are usually got to do with the distribution of the input bits and the spectrum that it will induce on the final modulation signal and all that, right. So you want your signal to be random looking and all that, so you do a lot of that to the message. Then when your code, if all that disappears, then you are getting a very bad spectrum for your modulated signal. Okay, so you want to control that, then systematic is important. Okay, so you want to have a good the same thing appearing after your coding also. Okay, so for that also you need, turns out you need recursive convolutional encoders. That is one thing, and of course the other utility is that it's a major ingredient in the turbo codes. Okay, so we'll see that later. For now we'll do this. Okay, so to get a systematic form, what should I have? Okay, what will be needed if I need a systematic form in the G of D? You need a 1, right? I need a 1. Okay, 1 will give me systematic, right. Remember, what is this? This gives you two outputs, V1n equals un plus un minus 2 and Vn2 equals un plus un minus 1 plus un minus 2. If I want it to be systematic, I want Vn1 to be equal to un itself. Okay, that only then I will get a systematic form. Okay, but remember it is a vague kind of systematic form. How am I transmitting it? I will do systematic parity, systematic parity, systematic parity like that. Okay, it is not like block codes where you have all the systematic bits occurring together and then the parity. Okay, so that is a slight difference, but anyway that is good enough. I am having the message bits in the explicitly in the code word. Okay, so I want 1 here. Okay, so how can I get a 1? Okay, so I have to divide, right? So that is the idea. So you have to divide, and that means you have to introduce some feedback in your shift register. Only then you can divide. Okay, when you want to divide by something, you have to do a feedback shift register, right? So feedback shift registers do division. And looking at these two, what do I think? What do you think I should divide by? It's dividing by 1 plus d square looks a little ugly, you know. I mean, then you can divide and actually do something, some simplification. But if you divide by 1 plus d squared, it seems like a minimal form. Okay, so maybe that's a better thing to do. But of course, there's a rigorous justification for why you might want to divide by 1 plus d squared. But anyway, so here's the systematic version. Okay, I will call it GSD just to distinguish from that. I will make it 1 plus d squared by 1 plus d squared and 1. Okay. If I do this, then I have a easy formula for Vn2. Vn2 is what? Un. What will I do for Vn1? How can I write Vn1 now? Okay, so there will be a recursive definition. So I think you have seen this in one form or the other if you took a digital signal processing course. Okay, you would have seen it as an a representation for the IIR filters, right? So you have a numerator and a denominator. Simply replace d by z, and then you will see everything happening. So if you do that, you have to write down a recursive definition. It is going to be Vn1 plus Vn minus 2 1 is going to be equal to Un plus Un minus 1 plus, did I get that right? Or the other way around? Other way around, okay, so I knew that was wrong. Okay, so it is going to be this way, Vn plus Vn minus 1 1 plus Vn minus 2 1 equals Un plus Un minus 2. Okay, so I have to do a FIR filters. A systematic form is very easy for Vn2, but for Vn1 I have to do a IIR kind of filter implementation. Okay, so it's a recursive implementation. It gives you that. Okay, is it okay? It's clear, right? Okay. First of all, it's not even clear to me, at least when I see it just like that g of d and gs of d generate the same code. Okay, so you remember if I think of the if I give k bit input and then I terminate to all 0. Now terminating to all 0 will be complicated for the non-systematic, for the systematic form. I'll come to that come to that soon enough. But supposing I terminate to all 0 to all 0, okay, will these two codes be the same? If I look at it as nk codes, okay, I can do that, right? Will these two codes be the same? That is the first question I have to answer. Turns out they will be the same. That's another thing. But we have to check that, right? So we have to check that, and then do all those things a little bit carefully. Okay, so I am dividing by 1 plus d square. It's a little bit different. Okay, so shaking your head. You're saying yes? No. Okay. Okay. So first thing I want you to do is draw the state diagram. Okay, or maybe draw the trellis. Draw the one full stage of a trellis. Okay. So let's do that for the systematic form. For the non-systematic form, I've already done it. Let's do it for the systematic form. Take about a few minutes. It's not too complicated, but okay, what is my state going to be? Once again, okay, so maybe before you do the trellis, let me draw a feedback shift register implementation of this. Okay, and then you can do the trellis. Okay, so you have a input Un coming in. Okay, it turns out I can do it with 2D flip flops. Okay, you might have seen this in DSP classes. Okay, even then I think it's good to see division. If you have not seen division before, it can be a little bit confusing to people. Okay, it turns out this. Okay, if you look at what happens here, if you call it yn, what will yn be? So yn will actually follow this y of d equals u of d divided by 1 plus d square. Okay, it is easy to see that, right. So, this is yn minus 1, this is yn minus 2, and clearly yn equals un plus yn minus 2 plus yn minus 1. Okay, so, that is this equation. Okay, and how will I get a 1 plus d square on top? Simply take yn and then plus with yn minus 2. Okay, so, that will give you the Vn1. Okay, so, this is a very standard implementation of in DSP for the IIR filter. I think it is called type 1 or type 2 or one of those types. Okay, it is also there is also other names for it, observer canonical, controller canonical, all kinds of names for these implementations. The standard pictures for linear systems you might have studied at some point in time, but even otherwise this is a good refresher. Okay, is that okay? So, this gives you the required transformation. So, clearly it is a memory 2 4 state system. Okay, that is not changed. Okay, so how will the trellis diagram look like? That is the interesting question. Okay, it will look definitely different from the systematic case. Sorry, one state won't be enough.
Completely
Describe the trellis, right?
I mean, because it's output dependent as well.
So the definition of the state changes.
No. One stage is enough. And definition of state is yn minus 2 and yn minus 1. Yn minus 1, yn minus 2. It is not un minus 1, us minus 2. Okay, remember what is state in a digital system? Output of D flip flops, not successive inputs. They do not have any role to play here. Un minus 1, un minus 2 is not state. Okay, so that is the first change. Okay, so it is good that at least somebody pointed out. State is basically yn minus 1, yn minus 2. Okay, see, state is something that will completely give me everything else that is needed to compute the output given the input. Okay, so that is the way to think about state, right. That is the right definition in a general context. I have a system, I want to describe its state, so I should say everything that is needed to compute the output given the input. Okay, given the input un, what do I need to compute Vn1 and Vn2? That's what you need. Okay, think about it. Okay, so it's a little bit, if you have not drawn these diagrams before, it can be a little bit confusing. You know, do I use the previous value or the next value or okay. So the time it takes for yn minus 1 and yn minus 2 to propagate through the XOR gate, all that is very, very tiny. Okay, don't worry about that. You get a yn and then you shift everything. Okay, so it's something that you must have learned when you did digital systems, but suddenly when you look at it after a long time, it can be confusing. At least it confuses me, I will tell you that much. The next state is always confusing, right. So you have to compute yn. Okay, so you fix yn minus 1, yn minus 2, given a un you compute yn first, and then you can compute vn1 and vn2 very easily. Then the next state becomes yn minus 1. Okay, so you will not go very easily like in the feed forward case from 0 0 to 0 0 or 1 0, you will go to other states. Okay, so some strange things will happen. You have to look at it depending on the feedback connections, the next state will change. Okay, I am going to try and draw the Okay, so maybe it is not a good idea to draw it here. Maybe I should, let me see. Okay, this is the easiest part. Okay. Another thing that's very easy is this. Okay, if everything is 0, then no 1 can ever happen. Okay, so this is also very easy. Okay, I will tell you the method I use, which really helps me at least. Maybe you are very smart, you can look at it and figure out. The way I do it is, I try and write down explicit expressions for the next state and the two outputs. Okay, explicitly in terms of the present state and the input. Okay, so suppose your present state is S1, S2. This is your state, and the input is UN. Okay, what is output? Okay, Vn1 is a little bit difficult to write down. Vn2 is simply Un. Okay, what is Vn1? You have to compute Yn first. Yn is S1 plus S2 plus Un. Okay, and then you are again XORing with S2. Okay, so you will get what? Un plus S1. Right?
Yes, sir.
Is that okay? You will simply get Un plus S1. What about the next state? This is the present state. The next state, S1 will go to this guy. What about this one?
Yn.
It will be Yn, right? Yn is what? Un plus S1 plus S2. Okay, so that is the way. Okay, I try to write like this, and then for every state I simply plug in this formula. I will get my answer. Is that okay? This is what I like to do. Okay, there can be any number of other methods, and I am not claiming that this is the most efficient or the simplest or anything like that, but this method works. Okay, in an exam situation, maybe there will be some partial credits for this method. So you might have to be careful with this. Is this okay? This is clear, right? So that is all. This is what is being implemented here. Okay, so 0 0, from 0 0, if my UN becomes 1, then what will happen? My output will be 1 0, no 1 1, and then next state will be 1 0. Is that okay? Next state goes to 1 0, my output becomes 1 1. Okay, so in general, if you design your convolutional code reasonably well, then the two branches that deviate out must be separated by 2 Hamming distance, right? So you want to maximize your Hamming distance there. So when you get a 1, you should get at least 2. Okay, that is one thing to keep in mind. So what about 0 1? 0 1 and 0, what will happen? Zero 1 and 0 will go to
1 0
It
1
will go
0
to
1
1
0
right?
1 0.
Okay, so yeah. Okay, so I think maybe I should draw one of these things a little bit differently. Okay, another thing to keep in mind, again once again, in a well designed recursive encoder, the inputs coming into a particular state will be different. Okay, in the feed forward case, the inputs going into a particular state will always be the same. You can come to 0 0 only with the 0 input, but in a recursive encoder usually it will be the opposite. Okay, if you got in on one branch with 0, the other branch you will come in with a 1. Okay, that is a twist in the recursive thing, and if it is properly designed, usually it will be like that. Of course there can be tricks where you can violate that, maybe, I do not know, but usually it will be with a 1. Okay. So this one will be 1, and like I said, the minimum distance should give you 1 1, okay, and this one will be 0, then 0 0. Is that okay? Now you know the trellis by symmetry what should happen to the transitions. It is very easy to fix the transitions now, right. From 1 0 you should definitely go to 0 1 and 1 1, likewise from 1 1 you should definitely go to 0 1 and 1 1. Again in a well designed trellis all this will be true, okay. It will have 2 outputs from each state and 2 inputs into each state. I think in any trellis that will be true, okay. So you have to have these things, okay, and you find the output for one branch, you can find the outputs for every other branch pretty much, okay. It is just a question of figuring out the inputs and everything will work out very fast, okay. All these things are checks you can use in a, like I said, in an exam situation. Okay, any answers?
1 0 1 will go to 0 1 from 1 when 1 comes in and 0 1 will be the output.
Okay, so this is going to be 0 1 0 and this is going to be 0 and 1 0, 1 and 0 1, okay. So that is it. So with just figuring out one branch you can quickly write down everything else. Like I said, this is true in a well designed trellis, okay. If you did it carefully keeping minimum distance in mind, all these things will come out quickly like that. Okay, so all you have to find is just 2 branches, everything else will very quickly work out.
1 to 0 1 straight you gave input as 0, is that correct, sir? 1 1 to 0 1,
Yeah.
hey, 0 1 to 0 0 is 0, who is this 1 1?
Correct,
That is
I think it's correct.
Oh.
See, the thing to remember is I think I compared with the system the non-recursive version. It does not mean that when you go from 1 1 to 0 1 you should not have input 0, that is not the condition. The condition is when you are coming into 0 1 there will be 2 paths and they will take different inputs. One path will have input 1, the other part will have input 0, that is all. That is the only thing to remember, okay. It is not that 0 is not allowed. So this kind of confusion, for instance now if you did not bother to do it and if you do not bother to work out some example like this in the tutorial sheet, you think okay it is just simple binary stuff, I can do this in the exam, believe me you will go wrong, okay. So this is some really tricky stuff, you have to be very calm and cool when you do it, otherwise it is very easy to make mistakes. Is that okay? I am sorry, somebody had a question, you are saying something is wrong here?
No, you're saying open book. So.
Open book.
Does not make
Will not get the same one, okay. Is that okay? Any questions on this? Okay. So now the next question I want to address is termination, okay. So let us address the termination part. You are starting with all 0, you clock in k input bits, okay. Suppose you came to the left part here, okay. How will I force myself to all 0 state? Okay. So it is a little bit more confusing, so let us do that carefully. Oh my god, what did I do? Okay, so let us do this. Okay, so let us address the termination part. It is quite easy, it is not that complicated, except that it is best to start from the all 0 and then work back, okay. So if you go from here then it might be a little bit confusing. So you can get to the all 0 state from 2 other states. What are the 2 other states? 0 0 and 0 1. So after one input I should definitely have only 0 0 and 0 1, I should not have anything else, okay, right. Is that okay? So, how will I go from here to there? These things are not too bad. I will have an input 0 here, and then I will have an input 1 here, right, 1 1 here, and then from 1 0 I will have an input 1 here and 0 1, and from 1 1 I will have an input 0 here and then 1 0. Is that okay? So, that will be the input, and then 0 0 is okay, you put in 0 0 0, and from here you go with the 1 and 1, that is all. Okay. So, the point is 0 termination does not necessarily happen with 0 input. Okay. So, you need to figure out what input you need to drive it back to all 0, and that will be also either 0 0, 1 0, 1 1 or 0 1. Okay. It will be any one of the 4 possibilities depending on which state you are in. Okay. Depending on which state you are in. Okay. After k input bits you will be in some state, all you have to do is have a lookup table saying if I am in this state I have to clock in these things, if I am in some other state I have to clock in these, you do that you will go back to the all 0 state. Okay. There is no problem there. This is last stage, and then you do the termination.
So, but in the previous case, I had an input, I just appended it with all zeros and sent it. Now, depending on the message bit, I could have been in any of these states.
Yeah, that's right.
So, does that mean that only when I know which state is I?
Yeah, so you have to do it, so you can't figure out the bits you have to append ahead of time. You keep clocking it out, and when you come to the last bit you know the state, then based on the state you can do it, it is not a problem. So, next question is a little bit more interesting. Is this the only way to 0 terminate? Is this unique?
Shortest.
Largest.
Shortest, is it unique?
Oh, you can take that to a 1 1 and then.
Yeah, I mean you
0,
can do
0.
some tricks, right. See, for instance, from 0 0 itself I can come to 0 1 and then come back to 0 0. I mean, if you want to be a little bit more crafty, or from 0 1 I can stay in 0 1 and then come back to 0 0, but clearly from 1 0 and 1 1 I can't play those tricks. Okay, if I try anything else it will not work. So, from 1 0 and 1 1 it is fixed. Between 0 0 and 0 1 you can do some minor trickery, it will not change anything, but it will still go back to all 0. Okay. As long as you pick one thing and stay with that you will be okay. Okay. If you keep changing it around then your decoder will get confused. Okay. So, you have to fix something and stick with it. Okay. So, this is one thing which is, this is the simplest thing to fix. Okay. Usually fix something like this, it will work without any problem. Okay. Why might you want to do something else? Just to
Be sure of the termination.
so maybe you don't want to, I don't know, I mean you shouldn't be doing that, don't do anything else, just use this will work. Okay. Alright, so 0 termination is one thing I wanted to mention. The other thing I wanted to mention is the equivalence between the systematic form and the non-systematic form. Okay. So, let us look at the non-systematic form where g of d was 1 plus d squared, 1 plus d squared. Okay. Okay, and then the systematic form where I suddenly have 1 plus d squared by 1 plus d squared and then 1. Okay. So, remember how do I describe the code words that I get? Okay. So, code words that I get are if I want to talk about a v of d, it is going to be 1 plus d squared times u of d and then 1 plus d squared times u of d. Okay. Then what will I take u of d here to be? U of d is degree less than or equal to k minus 1, right, that is all. Any polynomial with binary coefficients, degree less than or equal to k minus 1, I am going to get a valid v of d, then you play around with that, you will get your answer. Okay. What can I do here? Can I say something very similar here? What happens to v of d here? Vs of d, I am sorry, you get 1 plus d squared by 1 plus d squared times us of d and then us of d. Okay. Remember, I also want to zero terminate, right? I want to zero terminate, which means what does zero termination mean, by the way? Vs of d will eventually go to 0 after a certain point, after exactly k plus mu minus 1 stages, Vs of d is going to be 0 always. So, which means the polynomial, as a polynomial in d, Vs of d has finite degree, it is not a rational form or anything like that, it is finite degree polynomial. Okay. So, what should happen to Us of d now? I cannot have an, I cannot have an arbitrary Us of d of degree, all possible Us of d of degree less than or equal to k minus 1 I cannot take. I should take Us of d to be a multiple of 1 plus d square, only then it will work. Okay. And then one multiple of 1 plus d squared, but then what degree? What degree?
K plus 2.
I can always go to k plus, right, k plus 1, right, I can go all the way to k plus 1, so k minus 1 plus 2, okay, I can add the mu, okay, k plus mu minus 1 I can go to, okay, but it should be a multiple of 1 plus d square. Is that okay? So, I have to take Us of d, I will write like this to say a multiple of 1 plus d squared, degree less than or equal to k plus 2 minus 1. The reason I am writing it as k plus 2 minus 1 is to bring out the memory explicitly. If memory is mu, it is going to be k plus mu minus 1. Okay. So, once I interpret it this way, both the code words will be exactly the same. Okay. If I do not do zero termination, then things will become more complicated. Okay. I cannot say talk about equivalence between these two things, because I am doing zero termination, both will be the same. The only thing that has changed is what? My Us of d now is becoming a multiple of 1 plus d square. How is that possible? I mean, my input data can be anything, no? How is it always a multiple of 1 plus d square? That is what you are doing in the zero termination. Okay. So, if it happens to be not a multiple of 1 plus d square, you have to add enough things to make it a multiple of 1 plus d square. Okay. So, you are doing it by some division with remainder kind of thing. Okay. That is the idea. Okay. So, it all come together if you know something about polynomials, but even otherwise it will work out.
Then we can actually find out, if I know my input string, I can find out what I should find.
Yeah, that is what you are doing when you do the encoding. See, the shift register actually does a division, right? The input gets divided and finally you will be left with the remainder, and that based on that remainder you are going to figure out what needs to be added to make it a multiple. Okay. So, that is the idea. Alright. So, in the non-systematic case, you do not have to do any such fancy thing to figure out the encoded code word, you do not have to do anything. Here you have to actually terminate carefully, and that terminating carefully, all that you are doing is making the overall input stream a multiple of 1 plus d square. That is another interpretation for the same thing. Okay. That is all is happening. Alright. Sounds interesting enough, no? It is not too terribly interesting, but anyway. Okay. Some things that are more interesting is, so what has happened now is the mapping from input to output has changed, right? Mapping from input to output has changed, but the list of code words itself remains the same. Okay, you have not changed the list of code words, you have only changed the mapping from input to output, and in fact the input itself changes in a weird way, right? Initially when you do the input, you think of the first k bits as input and the last 2 are fixed. Here you have to think about it a little bit more twisted, the termination also is important, okay, you have to play a role. Okay. Some things that are interesting to note here, which plays a crucial role in the turbo code idea, is if you have a length 1 input, weight 1 input, okay, if u of d here is weight 1 on the in the non-systematic part, you will get a very low weight code word. Is that correct? Right? If u of d is just say 1, then you simply get 1 plus d square, 1 plus d square, weight is just 5. Okay, again in terms of the trellis, what does it mean to have a weight 1 code word? Weight 1 input message, you are deviating only once from the all 0 state and then you are going back again. Okay, so that will give you a very low weight code word. What will happen here if you have a weight 1 message, maybe somewhere in the beginning? Okay, what will happen here in the systematic case? Systematic case, what will happen?
It will end only when you terminate.
It will end, yeah, so you will get a lot of output code weights till you terminate, okay. See what will happen if you US of D, if your initial message is just 1 and all are 0, then you will terminate, right. So your US of D actually will be a very high degree polynomial, right, it will be a huge degree polynomial that you are going to divide by 1 plus D squared, so it will give you a lot of ones, okay. So it is like an IAR filter, impulse response is going to go on and on forever, it is like an infinite impulse response that is happening till you terminate. When you terminate it dies, okay, but otherwise if you just have an impulse it is going to give you an technically an infinite sum, but of course in final practice you are going to terminate somewhere, okay. But if you want to think along with the termination, then you have to say that US of D, even though there is a 1 here, it is actually a very high degree polynomial because I will put ones somewhere at the end, and so that high degree polynomial is getting divided by 1 plus D square and I will get a lot of ones, okay. That is another way of thinking about it, but essentially a better intuition is to think of it as a IAR filter, okay. I have an IAR filter here, so if I give it an impulse I will get actually an infinite amount of output, okay, till I terminate I will keep on getting something, okay. So I will get high weight code words, okay. So something is happening here with weights, okay, and that is what is interesting in the turbo code context, okay. So we will stop here for now, pick up from here tomorrow.